Roland. He's highly qualified, as you're going to see, he's a top scientist, and he's had a slew of just like highly prestigious position. I'm going to go through that, and I'll try to be as quick as I can. The list is very, very long. So number one, we have Director of Research at the CNRS, which is the French government agency for scientific research. And then we have currently Director of Research at the EPIDAPO lab. And that's very interesting because it makes epigenetics and then data science and then politics science. So that's kind of a joint venture with George Washington and CNRS. So as we can see, Roland's career has been highly interdisciplinary and highly international. Then currently he's holding an appointment as visiting professor in the Department of Physics at Georgetown University in Washington, DC. In addition of that, he's a co-director of Complex Cities, which is actually an international interdisciplinary effort that is bringing together two countries, France, US, also two continents. We have Europe. And the idea is really to apply this concept of urban physics, which is highly interesting. The idea is to see city textures through the prism of statistical physics and apply this to investigate environmental, public health, and climate challenge. That's actually very relevant, especially if you think of just like issues of social justice, for instance. And that effort is linked to users, which is another international venture where users stand for urban sciences and engineering for resilience and sustainability. And it is an international CNRS research network. In addition, Roland is the Associate Vice President for International Relations in charge of US and Canada for the University of Paris Sciences and Lettres. So you can see like we are adding leadership in addition to international in this case. And from 2012 to 2020, and that is how I came to meet him, he was the founder and head of the MIT CNRS Joint Laboratory of Multi-Scale Material Science for Energy and Environment. So when Roland is not busy founding and leading high impact international research center, he is a highly prolific scholar with more than 230 peer-reviewed papers published mostly in Nature, Science, and PNAS. So we really have a high caliber. So I'm almost toward the end. So in terms of his training, Roland received his master in plasma physics from Aix-Marseille University in France, and then a PhD in chemical physics from Imperial College in London, and then his habilitation degree, which is, I think, the equivalent of tenure in physics from the University of Orleans. So in terms of specialization, he focuses on bottom-up. So bottom-up is the word I learned at MIT. Bottom-up simulation approaches in the energy and environment, looking at problems such as CO2 sequestration, shale gas, cement and concrete research. One last thing, Roland, I'm already pre-booking your calendar for the next 2 to 3 years because you have to come back and talk to us about urban physics. Yes, so okay. I'm already pre-booking your calendar. All right. And now from a personal point of view, for me, Roland is family. So when I was growing up at MIT with my cohort from the MIT CS Hub and MIT Eggshell project, we spent countless evenings and afternoons at Roland's house, eating amazing food, playing music, and wondering about the meaning of life. So without further ado,
I cannot hear you anymore. Can you hear me?
Yes.
Yes.
Yes. Okay. All right. Thank you. Thank you a lot, Marie-Anne. I mean, yes, I'm busy guy. Yes, but I'm still, very much into research, really. As much as I can, and actually today I've made the choice to come to not to talk about cement because I did that already when Zdenek invited me some years ago, but I wanted to stick to what I like very much, which is statistical physics, and to apply that to this shale gas problem. Okay, it's not really civil engineering, but it has to do with civil engineering anyway because it's about the exploding shale gas. And actually, the whole thing of this idea of doing shale gas simulation in this bottom-up way that you were mentioning, Thérèse, is really to link statistical physics to an applied problem like shale gas. But the thing is, in the title, This is the fabrication of kerogen. So kerogen is really the core of shale gas, is where the treasure stands. This is where the methane, for instance, lives. So in this porous carbon, you have those methane molecules hanging around. And this is this fluctuation or fracking problem that connects those pockets. And this is the engineering of it. But what I want to tell you today is more like, how can we use a molecular simulation type of approach, which basically is at the scale of 1 nanometer and maybe 1 nanosecond in time, and try to do a prediction or to understand the formation of those kerogen, those phases that contains the gas, that actually took something like 300 millions of years, which is a long time. So you see the discrepancy between 1 nanosecond and 300 million years. There are like a few orders of magnitude there. So what can we do with the molecular simulation thing? Okay, this is an effort at MIT that actually started, the slide don't move. Uh-oh. Can you hear me still? Yes, yes, okay, I don't understand why the slide don't move. So I end the show, I will start the show again because, all right, I don't have the slide moving, so let's do it. All right, so is it better now? Let's see if it moves. All right.
Roland, can you do full screen? Go full screen.
Okay, okay, all right. Let me just, because I have several screens connected.
No, and then you can swap it. So go from full
Maybe
screen.
let's see if it works. Yes, I think so. All right, so okay, maybe now I have the co-authors of this work, and you see the large series of colleagues. This is the first top list is colleagues and professionals from France and obviously from the US. Recognize Franz, for instance, but many of them were with me at the joint lab at MIT actually during like 10 or 12 years actually. And also a lot of students were involved in this shale gas research with the sponsoring of different companies from Total, Shell, Schlumberger over time and so on. And we think, I mean, we made some kind of pretty progress in the sense of understanding what it is. So this is here, you see on the top row, on the top left, the well, okay, there's the pipe vertical going down, and at some point you turn horizontal, and this is where you do the fracking jobs. This is those fractures that you can see in the red regions. And to connect the pipe to those tiny pockets of porous carbon, this is the middle, the central picture, where you have this kind of very disordered, porous, multi-scale porous carbon. And if you zoom into the nanotexture, the nanoscale, because the central picture is at the scale of microns, you zoom down into the scale of nanoscale, and then you find out that I will show you that, but that whole thing is made of a nanoporous carbon with pore at the scale of 1 nanometers. You see, there we are dealing with a kind of complex material with a multi-scale porosity, obviously like cement, if you like. And obviously in terms of production, it's all related the way those molecules, those alkane or methane molecules, to speak simply, are actually diffusing in this complex system, right? So this is typically what I'm going to try to address today from a molecular simulation perspective, and also the making of those kerogen. All right, so if you open any books on shale gas or geochemistry, you will find this kind of plot. This is called the Van Crevelen diagram. This is on the y-axis, the hydrogen to carbon ratio. This is really on the chemistry of those kerogen. And on the x-axis, this is of the oxygen to carbon ratio. And actually, the geochemists have kind of ranked or classified that actually there are several types of kerogen depending on the pristine molecules like back 300 or more millions of years ago. If there were trees or algae or whatever, well, animals, whatever, they produce different type of kerogen. This is the 1, 2, 3, 4 types. For instance, charcoal is really type 3, right? And you see, over time, those organic molecules, they go in time, they get buried in time, and of course, the deeper they get, the temperature is increasing. So there is a cooking of those molecules called pyrolysis. Pyrolysis is a cooking with no oxygen. So basically, we are removing oxygen and nitrogen and sulfur. At the end, we're left with a backbone structure, which is porous. So when over time, you go down and to the left. So at the end, you see that we have no more hydrogen, no more oxygen. So we have a plateau where at constant hydrogen, we are losing oxygen, and then we go down where we are lost our oxygen, and now we start losing hydrogen. Actually, this is the production of those hydrocarbon molecules. So that's typically this kind of thing. And that, okay, there is no time scale there, but from the plateau on the right down to 0, it takes, as I said, hundreds of millions of years, which is a lot. All right. Now, obviously, people have been very much into the texture of those. This is here an SEM or a FIB-SEM, so it's a 3D representation at the micron scale. So the box is actually, you see a few microns, and you can see in yellow, I kind of picture the interface between those carbons, between the pores in the carbon. You see clearly we can see that there is a big crack at the scale almost crossing the box, but we have some smaller pores, and actually even smaller pores. And I will show you that when it's in the gray, this is already also porous, but at the scale of nano. All right, so this is the question I want to ask is, I mean, really, what is the nanotexture of kerogen, and what are the implications in terms of transport properties, maybe mechanics of those, and so on. All right, at the nanoscale. But if you, obviously we can go along and try to find an analogy, and this is what people have done. If you compare a mature kerogen as on the left to an activated carbon that is produced for the industry, you have a lot of similarities, So you can see at the scale of nanometers, because we are at the scale of nanometers when we use TEM, that we are something which is close of a nanoporous carbon that we fabricate every day on Earth for whatever filtering application, for instance, okay? Except that the natural one took, as I said, a long time to cook. All right. A bit of statistical physics. You cannot avoid that with me at some point. I'm sorry, but okay. If you are to do a whatever, a liquid, a gas, a solid onto a computer to try to understand the properties, and you apply the rules of interaction between atoms and try to average those way those atoms are arranged together, in what you call configurations, then you are straight into the field of statistical physics. Numerically speaking, what we do with simulation, we do simulation because we have no way to solve this theory on the paper with a pen and a piece of paper, just because there are too many degrees of freedom in the system. All right, so we're bound to do some numerical application. So there are two ways to solve the statistical physics problem. Either you do it as by generating configuration in a kind of random way, a clever random way. It's not really clever. There are rules there. It's called Monte Carlo, and you can do averages. Or you take a system, and this is what mechanicians love doing, because you do apply the rules of Newton, Newton's rules of motion, and then you solve the molecular dynamics. Okay, maybe at one point you should say, okay, how can we apply Newton's rules to an atom? Because an atom is supposed to be quantum, so we should be applying quantum mechanics, not classical mechanics. And actually, the answer is that it's not that we decide of that, is that there is a criterion which is called, which is a length scale, okay? And this length scale is a kind of frontier that depends on the mass and temperature, that tells you if the length scale is on the scale of the molecules or the whatever, the atoms, then is on the other, then you should apply quantum mechanics to solve the problem. But if the temperature is high enough, the density is not, I mean, the mass is not too light, so big fat atoms, then you're safe, because this length scale is called the de Broglie wavelength, will be way smaller than those characteristic lengths of the system. So then you're safe with Newton mechanics. For instance, water at 300 K behaves like a classical body. Hydrogen at 300 K is a quantum thing. All right. Right, anyway, so what's important here is that, okay, we are in the scale of classical mechanics, fine. With Monte Carlo, we generate those configuration in random way, and then we average over them. So specify the ensemble. That's the constraint in terms of, do I have a constant volume? If I have a constant volume, then I can calculate the pressure as a conjugate variable, for instance. If I have a constant pressure, then I can calculate the volume. That's an example of those conjugate variables. That these are constraints that specify a statistical ensemble. But then we average the thing, and either of a number of configurations for Monte Carlo or other time in molecular dynamics. So on one case, we do ensemble simulation, ensemble averaging, the other one we do time averaging. But what is important there is that if you do enough configuration or a time long enough, then the answer is the same. All right, so there is no like one better than the other. I mean, at equilibrium, at least, they should give you the same answer. At equilibrium, because why? Because mechanics could be applied out of equilibrium. Monte Carlo is specifically designed for equilibrium. All right. let's apply that thing to organic matter. So mimicking the production of kerogen. So as I said, between the scale of molecular simulation and the real scale of the geochemistry, there are maybe some orders of magnitude. You see, between 10 to the 13 seconds to 10 to the minus 8 seconds. We start by piling up significantly some orders of magnitude. And so the question is today's statistical physics in this numerical version, Monte Carlo or MD, molecular dynamics, able to do something to be relevant to answer any of those timescales? I'm talking the geological timescale. The answer is yes, and the answer is with the advanced what's called advanced molecular dynamics, if you like. And one of them, for instance, is this replica exchange molecular dynamics. This is all part of a family of techniques called metadynamics. This is one of them, okay? So basically, what we want to do is to accelerate time. But you can tell me, okay, but easy guy, if the easiest way to accelerate time will be to run a simulation at super high temperature, because obviously you will accept more steps into a Monte Carlo procedure. You will have larger velocities into simulation. In MD simulation, obviously you should go faster and simulate time. Yes, but when we are dealing with chemistry, changing the state condition, temperature, for instance, you may change the way the reaction proceeds. So maybe the reactant will go to different products because of that. So we should find a way, and see, we are dealing here with chemistry. We are transforming molecules. We have to remove, to break bonds, right? Because as I said in the Van Quevelen thing, we are removing oxygen and hydrogen. So we should be able to, we have to keep in mind not to mess up too much with the chemistry. So this is the idea of this replica exchange molecular dynamics, or it's also called parallel tempering. And we use it with a reactive potential. So now I come to a second point. I tell you a bit about the statistical physics. We need at some point to describe interaction between bodies, right? All right, they have different ways to do it, different theories and different functions, okay? And they are more or less complex, but they are supposed to mimic the real thing, right? And when we talk about breaking and making new chemistry bonds, it has to do with electrons. And as I said, I mean, continue discussion about quantum bodies versus Newton bodies, an electron is always a quantum body. So we should be doing quantum chemistry to understand the chemistry, right? Hopefully not, because now over time, people have developed what's called reactive potential. So for just the type of molecule we're going to deal with is we're going to start with this is typically wood, right? Cellulose and lignin. This is a molecular structure of cellulose made of carbon, or hydrogen, and oxygen atoms. Same for lignin. And we're going to try to age those molecules, all right, with those on the computer and simulate 300 million years. Right, so, and as I said, we're going to apply this replica exchange molecular dynamics is one thing, but then we need to describe the interaction, how those oxygen atoms and carbon and hydrogen are bound together to form those molecules. And then, okay, as I said, we should be at quantum. Quantum means these days DFT, density functional theory, the quantum one, okay, to do the business, to manage the business of electrons. But this is very restricted in size. You see, the cube is very small. These days, a proper DFT calculation can maybe take on a few hundred of atoms. If we want to simulate a full, like a micron size of kerogen, we'll be dealing with maybe 1 million of particles. And now we cannot do it in the quantum way these days, even with the fastest computer. So this is why people like Adrie Van Wyn, is a professor at Penn State. It's very famous to have found a way, analytical function that mimic the quantum. And it's called reactive force field, REACT-FF. So we have an analytical function that describes interaction between carbon, oxygen, and hydrogen, and the way they can break and form bond, for instance, or okay, whatever. So the idea of this REACT-FF, and it's not the only one, by the way, reactive force field available now. There is this IREBO potential in 20 years ago, say that REACT-FF is famous because it has many elements of the Mendeleev classification of elements. So the whole ideas of those reactive force fields that they use what's called a bond order, which is this concept that is you're analyzing constantly for every species, every atom, the surroundings. If I'm a carbon atom and I'm linked to I have some carbon atoms. I have three ways to do bonding. Okay, according to chemistry, to organic chemistry, right? So, and the bond order is actually taking, this is a way to translate that into a function to analyze the environment, so that I can decide that, oh yeah, I have this kind of density around me made of oxygen. I'm going to do this kind of bonding with those atoms. Okay. All right, so this reactive force field, say, is mimicking the business of electrons, so that we don't have to do a quantum calculation, because otherwise we'll be stuck with doing 100 atoms. Right? All right, so I'm going in the right direction. Where is it? Up. All right. Sorry, I'm a bit here. Yeah, what is it? All right. All right, now let's go to this replica exchange. As I told you that we're gonna do high temperature without messing up the chemistry. How do we do that? Okay, as I told you, I mean, this replica exchange is called also parallel tempering. So it means that we're going to use a parallel computer. Every processor of that computer is handling the same configuration, but at a different temperature than the nearby processor. Different is not too far away temperature. And if you look at the classical physics of things, when a liquid, a gas, if you look at the way the energy in the liquid, for instance, at a given temperature distribute, you have this Gaussian distribution on all possible states of the liquid. All right. If you now do the simulation at temperature just lower, a bit higher than that given temperature, you have another distribution, a Gaussian distribution of energies. But because temperatures are not too far away, you can see that those configurations actually overlap. And that's the key thing, because it means that in the overlapping region, configurations that exist at a given temperature can also exist at a temperature a bit higher or a bit lower, depending on which side of the histogram you're on, right? And that's very interesting, because it means that the configuration that was cooked at T1 can be passed on to the configuration to the processor that is handling the simulation at T2, T2 being like 1 or 2 degrees away from T1, all right, with a probability of existing. And this is what is written at the top of this equation. This is the acceptance probability. This is a very Monte Carlo type of approach that tells you the probability of exchanging a configuration at UI energy to a processor that is managing the simulation at Tj with a Uj energy. This is very simple. We calculate 1 over the reciprocal of temperature, the difference of those, times the delta of potential energy, and we compare that this quantity with a random number taken between 0 and 1. And the Monte Carlo procedure is very simple. If that exponential, this Boltzmann factor is called, is actually larger than the random number, then we accept the move. If not, we reject the move. And then we proceed this way. So basically, we are exchanging the configuration from high temperature to lower to lower and lower temperatures. In the end, we want to observe the observation temperature is the one we choose, which is typically the lowest temperature of the different temperatures that we are considering for all the processes. And that's very cool, because with that, because of this overlap of probability in between the histograms, then we are sure that the chemistry is still good. Right, we are not biasing the chemistry with a high temperature, because we're exchanging processor by processor, temperature step by temperature step towards in a realistic way, and that's the probability of exchange right now. All right. Now, all right. So maybe I have a movie there. So hopefully it's going to work. So this is cellulose. This is a very small sample just for the purpose of showing you the way it works. So we start with the full configuration. This is, you can see in green the carbon, on red the oxygen, and white hydrogen atoms. This is a molecular crystal of this kind of polymeric molecule called cellulose. And we're going to cook it in time. And this is, we're going to show it, we're going to show some blinks in the movie. This is every time a configuration is reaching the lowest temperature. So, and then as we go on with the movie, you're going to see the making up of a, sorry, where is that thing? The making up of a carbon backbone and some other molecules. All right, so we can shape, and you see the destruction as we move of the molecules, and the more and more green are linked together, carbons. At the same time, okay, it goes too fast, but if you analyze, you can see some water molecule being produced. You can see CO2 molecules were being produced, CO and hydrogen molecules, all right? Or maybe I don't have time to wait for the end of the movie, so maybe I can jump to the last configuration. It's really like we are, and with this spiral exchange thing, we are accelerating time in a kind of compatible with chemistry without messing up the chemistry. And you can see here already we form a longer chain of carbon now, okay, and so on, and even some aromatic rings, like, and so on and so on. So let's go to the next slide, which is in this case the final thing. So basically now we have a big chunk of green, and flying around, maybe you can see some water molecules and so on. So this is a very small sample for the sake of showing you the way it works. Obviously, we do it with a much bigger system, but now the problem with the technology somehow is that, as you know, as the system gets bigger and bigger, then those histogram of energy configuration gets narrower and narrower, meaning that to have a proper overlap, we need to have temperature differences between two processes kind of small in a fraction of a Kelvin. So it requires a lot of simulation, but at the end we can do it with these days processors, because we can play with thousands of processors. All right, now we can try to analyze the different the different molecules form. So let's start with the light ones. You see, as the time of the simulation, is moving forward, then we can see that we have the production of hydrogen, water, CO2, as I said, right? At the same time, after a decrease of the carbon backbone, you see the drop on the bottom plot, you have a regrowth of a phase made of carbon, right? This is the backbone growing up of things that will be, in the end, the porous kerogen, as we will see. Right, so then we can compare lignin and cellulose, for instance. Clearly, lignin, these are the squares, for instance, and cellulose are the circles. We produce less water with lignin than cellulose, less CO than lignin with cellulose, and so on. Okay, and this is typically linked with the structure of the pristine molecule in the first place. Okay. All right, so then we can go further with different molecules, and obviously the methane is very, very, very interesting, because we see this time that actually lignin in the squares, actually we produce way more methane than cellulose. Cellulose is not good; it's not good shell gas, if you want. All right, lignin is way better. All right, for instance, just to tell you that. And then, okay, and the chemistry is not only that simple. We can build more and more complex molecules, you know, those kind of 2 carbon containing molecules, and we can analyze to 4 or whatever. Obviously, when we go, okay, we can do the histogram, and the way the things is producing, the simulation is producing, as I said, hydrogen, water, CO2, and CH4. Obviously, in terms of what? In terms of industry, they are looking for the molecule that are producing the largest amount of CH4, of course. Right? So, of course, charcoal is not a good thing. But CH4 is part of the picture. We all have known about those accidents in charcoal mines because of methane, right? Those explosions, right? It's typically over time, those pockets of methane is produced by the kerogen and so on, by carbon, charcoal, and so on. All right, so let's analyze the texture of the carbon phase. As I told you, what we're doing is producing a lot of tiny molecules, but also, and then the carbon is kind of gathering the atoms gathering together and form a bigger structure, which is on the right, for instance. And you can see, for instance, rings of six carbon. This is aromatic rings. Typically, that at the end of time, some of those molecules can be again to graphite or graphene, actually. All right, we can do it synthetically now these days, of course, but this is the same carbon chemistry. What's interesting, as I said at the very beginning, this reactive thing is a way to decide what kind of bonding I'm doing in the system. And actually, if you look at the chemistry of carbon, there are three ways. Either a carbon has 2 neighbors carbon, it's called sp bonding, or a carbon has 3 neighbors bonding, like in the ring, this carbon ring there. It has 3 neighbors with very defined 120 angles, or a carbon atom can be bonded to 4 carbons, other carbons. This is sp3, and this is typically what we have in diamond. Diamond is carbon, right? But it's not graphite. Graphite is purely sp2, diamond is purely sp3. And you can see the way those type of bonding are evolving during the simulation. And you can see very interestingly that we start with something which is very much sp3 in the cellulose. Okay, every carbon, that thing that it drops down crazy. And then what we have is actually a production of the yellow, which is sp2, which is a three, every carbon are three, I mean, most of the carbons are three neighbors carbon, and in a very graphene-like arrangement, at least locally, right? Well, you can see there's a very defective structure, of course. All right. So where is the thing is this? I know, I think. Wait. All right, so, and then we go with the, maybe you don't want me to do this, right? And show. Yes, okay. Yes, so, sorry, where am I now? Here. Where was I? Here, not here. Yes, yes. All right, so now we can analyze further the cellulose versus the lignin in terms of the things. And clearly the lignin is producing a largest chunk of carbon. You see the C40 plus containing the number of carbons is actually bigger in lignins than cellulose. So cellulose is saying that it's producing smaller units of carbon, while lignin is more producing a percolative structure of carbon. All right, now let's come back to the beginning and the Van Crevelen diagram. So are we good in predicting? So predicting what happened in chemistry. So remember that the Van Crevelen was ranking or classifying all different type of kerogen, and we are clearly with cellulose and lignin doing type 3. All right. So we are really there, and then this is on the right, our simulation compared to some data from experiments. So we are very much in the ballparks of those experimental value for natural carbon and thing. But what's interesting is that the lab experiments that people have tried to reproduce in the lab experimentally, the pyrolysis, this cooking of organic matter over time. And they realized that they actually, and as we actually find from simulation, is that in order to refine the experimental curve, the natural production curve, you actually, in the lab, you need to extract the fluids as much on the cooking, those CO2, water, and so on. And that's a key thing, actually. And then we're going to understand why. Anyway, one way to validate is to take this carbon structure and calculate the heat capacity, for instance, from our simulation and compare to experiment. And you see the different sample that we have. These are the color points. Different colors mean different chemistries. So the yellow and red, they contain more carbon. So they're more like cellulose. The other one are containing mostly carbons, and they are more like closer to lignin at the end, to what lignin has become. But clearly we are on the experimental line, actually, that spans from graphite and diamonds up to alkanes. So this is really a way to look at that. And at the end of the day, if you look at the physics of that, we calculated the vibration. So this is really a way to somehow to probe if the chemistry is correct. All right, so as I told you, the fluid is important. So this is the end of our simulation on the left. So I can kind of extract the fluid, which is typically all those molecules, water, CO, CO2, and so on, and the kind of backbone of carbon, all right? But as I told you, the experimental was showing that we need to extract the fluid. So if we do that thing, there's all carbon structure actually collapse onto itself and ends up into this porous carbon structure. If we calculate the structure factor, so what will be experimentally the X-ray diffraction, we are very close to the experiment. And we can also do a look at the Young modulus or the reciprocal of it, the compressibility, and we are also quite close to experiment. All right, so now we're going to move into analyzing more those textures from porosity, density, and so on. And obviously, this is what cellulose has become when you remove the fluid. Next slide is the same for lignin, and you see that the textures can be different because lignin has more like a bigger chunk of carbon, right? In the end, creating bigger pores in the structure, while cellulose is actually more compact or denser. All right, so actually those, now we come back to very like my first work onto the porous carbon that was like 20 years ago with Keith Gubbins at North Carolina State University, and we're doing the first molecular structure of carbon. And at the end of the day, those Kerogen phases where there is not much of oxygen there are very, very similar to a porous carbon. This is very much what I said already when we were comparing TM to Kerogen, TM of charcoal to Kerogen. All right. So typically, those, as I said, the very introduction slides, that the nano texture is really made of this little box on the right, which is a nano porous carbon. The size of the box is 5 nanometers. You can see pores or fracture or whatever, voids, say, at the scale of 1 nanometer. Obviously, now we can be more quantitative and calculate the pore size distribution. So there are statistical ways to do it, basically inflating spheres, atomic, like in pores. And when you start touching the atoms, then you collect the size and you do the histogram. So that will be the pore size distribution. And we do that for the porous different Kerogen. So one with lots of oxygen, that will be the Marcellus, the Eagleford, the red one, or the blue one is actually the Marcellus, which is with very mature, not much of high oxygen left. And so this histogram is very much from, I don't know which one is which one, but yes. So the histogram is actually from experiment, from simulation, while the curve is actually from CO2 adsorption measurement. So we can access the pore size distribution by outgassing the sample and putting back some CO2. And the way to put it back at constant temperature is called to measuring an adsorption isotherm that is used for anything, any porous material, including cement. It could be nitrogen and CO2. And CO2 is especially good to probe this 1 nanometer scale. Anyway, when we do the CO2 adsorption and calculate the pore size distribution, we are right on the top of what the simulation is predicting, actually. All right, so that's going back to lignin and cellulose. You can see, as I said, that the cellulose is very compact because the pores are between 4 and 8 angstrom, not even 1 nanometers. While in case of cellulose, it extends, those nanopores extend maybe to 2 nanometers. By the way, this is what I will show at the end of my talk. This is not the end of the story. We are very much in the very nano scale of the porosity. Obviously, there is a larger scale porosity with larger pores anyway, right? But we were very investigating those. All right, what can we do with that? Actually, once we have the simulation of that, we can try to simulate the adsorption of gases into this thing. So this is another simulation technique. Still Monte Carlo is called grand canonical. So we fix the chemical potential, so the vapor pressure of whatever, methane, CO2 in this case, water could be, and see how much how much water will, or CH4 or CO2 will get into the pores for that pressure on the outside of vapor pressure on the outside. And you see, then we can plot the amount of molecules in the pore as a function of this outside pressure, okay? And then we can compare to experiments, and we see that the comparison, I mean, we are pretty close actually, right? For CO2 and for methane, we can actually kind of predict actually the adsorption isotherm with no issue. And there is not even a need for to this kind of reactive potential in this case, because this is physics option, so there is no need to describe chemistry. So a simple enlargement function kind of will work doing that. Okay. So just a comment, you see that the CO2 actually is having a cusp-like shape. It's great because we are plotting the excess adsorption isotherm, which is only to compare with experiment. Experiment always measures the excess adsorption. Excess with respect to what? To a box of the same volume containing no porous material. Okay, so this is the effect of the confinement, if you like. So this is, and we have a cusp because at the end of for this high temperature, because we are supercritical in the case of CO2, actually the density outside is larger than the density inside. That's why you have this cusp. But anyway, so we can predict the adsorption. And talking about prediction of something, we actually showed that those porous carbon love CO2. They don't like so much water, meaning that even if you calibrate with the pressure on the outside of liquid water at a pressure larger than the isostatic pressure in the field, the water will hardly get into the nanotexture of the Kerogen. By contrast, CO2 loves going there. And not only loves going there, but what does it do is actually it displaces methane molecule. So back 10 years ago, we were saying in the industry, you should use CO2 to actually stimulate the production of methane, because right now the technology, which is based on water, we do water fracking, this technology does not address the nanopores. The water just does not get too much into those nanopores, while CO2 does. Not only does that, but it kicks out the methane molecules and stay there, meaning that using CO2 to stimulate the shell production will be also a sequestration of CO2. So it could be, you can be paid twice to recover more methane, and you'll be paid to store CO2 that nobody wants because of this climate change thing, okay? All right, so that's a prediction from simulation. And then let's move now to the last part of my talk, which is very much onto the predicting the transport properties. So we did simulation of absorption of methane, CO2, and so on, and water, and blah, blah, but also we did a whole collection of different alkanes from methane up to dodecanes, okay, C12. All right, and we were trying to understand the way those molecules can actually move around the pore network and see if we are okay with the mechanics of fluid, for instance, right? Can we make some prediction out of the theory that we have for fluid? So first thing we're going to do, we're going to use MD, molecular dynamics this time. It's pure MD, solving Newton equation for those molecules into the pores of those guys with interaction. So we have interaction between the molecules and interaction between the molecules and the carbon strong that makes the matrix itself. And actually, we're going to apply an out-of-equilibrium condition. So we're going to give a force to the mass center of every molecule to make them to move in one direction, for instance, the Z direction. And that force will be divided by the surface of the box. That will be a pressure. So we are applying a pressure gradient to the simulation. And we can calculate how many molecules go through a surface area, that's the size of the box, per unit of time, okay? And so on. That would be a flux. So if we study the flux as a function of the pressure gradient, then we are studying the Darcy's equation. All right, Darcy's is this linear physics response theory where the flux is actually proportional to the pressure gradient. Fine. And there's a constant in between, I say proportional, and actually in the Darcy's formulation of the flux, this constant is actually the ratio of two quantities. K, which is the permeability, is expressed in per meter square. So this is typically a geometrical thing. So it's really a characteristic, of the porous material. The eta at the denominator is actually the viscosity, which is a fluid characteristic, right? So that we can get from, okay, we can calculate or get from data. Anyway, if we apply this pressure gradient and we plot the flux as a function of this pressure gradient for the different molecules, that we see is that we do have a linear response theory. Yes, we're still in the linear response theory. Very good. Meaning that, yes, the flux is proportional to the pressure. Very good. So there is a constant there, and the constant is K over eta. Very good. Okay. So let's calculate eta from statistical physics. So if you look eta from statistical physics, actually in the bulk, this is the what's called a Green-Kubo formulation. This is basically the self-correlation in time for given molecules of the pressure tensor. You calculate this integral, and this is the statistical physics formulation from the viscosity, fine, and we can compare with for the bulk with the experiment. I mean, yes, from data from NIST, for instance, and we are not crazy bad, fine. Meaning that if we know the flux, if we know the pressure gradient, and if we know eta, we can calculate the permeability for this nanoporous material. And as I said, permeability is actually a property of the material itself. It should not depend on the type of molecules in there, in the pores, or neither the amount of those molecules in the pore. So let's try to plot K as a function of a reduced quantity, which is this 1 over eta. So we have this flux divided by the pressure gradient, and that should be equal to K over eta. So we plot as function eta, so we should have K as a constant. And as we can see, this is not at all a constant. Not only depends on the type of fluid, it's different from methane to dodecane, but it also depends on the amount of fluid you put in the pore. So this Darcy's equation is actually not valid at the nanoscale. Okay, so you are wrong, Mr. Darcy. I mean, this is you are mistaken. This is in Pride and Prejudice book from Jane Austen, where there's the Darcy's guide there. But obviously not the same Darcy's who did the fluid mechanics, but okay, but you are mistaken. Mr. Darcy had the nanoscale, obviously, simply because the viscosity is not defined for one molecule in the pore, because remember that the pore size, that the scale of 1 nanometers, basically you have one molecule in the pore. That's not a fluid. So the viscosity is not, you cannot calculate, it makes no sense calculating viscosity, or the integral that I was showing just does not converge. So if the viscosity is not defined, then the permeability is not defined either. That's the big conclusion, okay? Okay, fine. So let's move to what we can do then. We can go back to a very fundamental equation. So we start from the linear response theory, where the velocity or the flux is proportional to the gradient. And now we're not splitting this constant that we call the permeance into the viscosity and permeability. We just stick it, we stick as one thing, one coefficient that we call permeance, and that actually we can show from physics that is related to the transport coefficient dc here of species I, and also the cross coefficient that between the two molecules or two species, which called the Onsager coefficients. But as I said, we are in a pore one molecule at a time, basically. So that second term is actually 0. So basically the permeance, this K, is actually, okay, equals to the transport coefficient divided by rho KT. Fine, super good. And not only that, we can show that the transport coefficient, this out of equilibrium thing, is actually equal to the self diffusion coefficient. And that's a very key step, because of this one molecule at a time idea, the self-diffusion equal to transport property, meaning that the self-diffusion coefficient is actually an equilibrium quantity. It's the amount of surface area every molecule per second where the mass center of the fluid doesn't move. But the transport thing is where you have a transport, the mass center of the old fluid is moving through the porous material. But in those conditions of nanopores, we can see that the self coefficient equals the transport coefficient. So basically, we can relate from an equilibrium quantity, we can relate to an out of equilibrium quantity. This is very interesting. And not only that, following actually de Gennes back in the 80s, nothing to do with shale gas. It's just he was studying the way polymers can actually diffuse in the melt of polymers, and he put down this free volume theory, which relates to how much of free volume is left for given conditions. And when we do adsorption, the free volume is actually the amount of space free in the pore. So we can actually relate the free volume to the adsorption isotherm I was showing you, the amount of fluid as a function of pressure, which is because we are in nanopores, that the gas can be fitted to a Langmuir adsorption isotherm. All right, meaning that, okay, there's no way you can study a phase transition, a capillary phase transition, those things. The pores are way too small. Anyway, we can actually predict, by knowing the adsorption isotherm, we can predict the self-diffusion coefficient that equals, because of those nanopores, to the transport coefficient. Then we can calculate the K, the permeance, then we can predict the flux. This is very cool, right? So that we can predict the flux by just doing an adsorption experiment at equilibrium. All right, does it work? Yes. So we see the same equation, plotted in kind of log way, so that we have linear behaviors. And actually, end of the day, we have two parameters in this thing. We have this alpha and the Xi0. The Xi0 is typically how much the molecule interacts with the solid, or this is a kind of friction, if you like. And the alpha is coefficient. And what's interesting, this is the work of a former postdoc, Amel Obligé, who actually gotten a position at CNRS now in Pau. With Gilles Pigeot-Descabeaux, that of course Zdenek knows very well. Very good, because Amel has shown that those two parameters, alpha and Xi0, actually are just depending upon the density, the porosity. Okay, if we have a porosity that is less than 20, that's around 20% at least, then we actually have, this is a linear behavior, sorry, with the density, with the porosity parameter of the thing. So if we can measure the porosity, basically we can measure this coefficient, one adsorption measurement, and we're good to go and predict the transport properties. All sounds very good, But this is not this is not the end of the story. Why is that? Because as I said, and this is my last, I'm a bit too long maybe, is that actually, as I said, the porosity is not only sub-nanometric. So we did some electron tomography experiment with colleagues in Marseille. I'm going fast through those slides. Basically, we can have a picture with a resolution of 1 nanometer or less, but 1 nanometer size, of different of those Kerogen samples to see the big pores. So maybe the thing are going to work. So yeah, you can see turning those boxes. So let's do this one, for instance. This is a piece of Kerogen from Eagle 4, which is this is a field in the US. When you can see that that sample with the size is 200 nanometers, the size of the box. And you can see a big pores in the center of the pore. And tiny, tiny boxy, tiny thing that we were studying up to now. Meaning that in those big pores, obviously, we do recover a Darcy's behavior. So the story is the following, is that we need to obviously to make accurate prediction to take into account those pores, right? So this is what we did. So we did a big simulation chunk of the nanoporous carbon called Kerogen, and we carved out, we digged into the pores that we actually measured from tomography experiment. We relaxed everything. So now we have a system that is actually Joe, in the sense that we have nanopores, sub-nanopores, and bigger pores. For instance, in this case, we have this big pores that is actually kind of there sitting in the middle of the sample. Obviously, if we are to have only nanometer pores, the self-diffusion coefficient will be equal to the actual transport coefficient. This is what we actually calculated. But when we put those in place, those big pores, this is not the case anymore. All right. But then we found a way to correct that thing. So it's still to relate the self-diffusion coefficient to the transport coefficient by measuring the amount of we have a linear relation with the amount of mesopores, the big pores, divided by the nanopores, the volume of nanopores. So that we can actually still use the free volume theory and so on. We're just correcting the free volume theory for the amount of big pores. With that, we are equipped to predict the transport. All right, so these are a few papers that we publish over time. Okay, and then I actually thank you for your kind attention. Thank you.
Thank you for an excellent talk. So join me in congratulating our speaker.
Thank you, that's fine.
So I'm going to open the floor up for questions.
Hello, Gianluca.
Well, I had a question about the Darcy's law. So I'm not at all surprised that it doesn't apply on that level, but if I understood the latter part and what you said after that, it would apply if you have these pores.
Yes.
And then my next question is, if you were to scale up to say the size of a laboratory specimen, would you recover Darcy's law? And if so, I think you were too harsh on Mr. Darcy.
Yes, yes. yeah. But the thing is that really the current technology, the amount of those nanopores is very large. This is a very key feature of the texture of those porous carbon. And the message to the industry was to say, you're not targeting you're leaving behind the treasure, right, of this shale gas exploitation, by not assessing the amount of nanopores where at least methane and so on molecules are sitting. So now is to make them to move. The first, to diffuse and be maybe recovered, is to diffuse through this network of nanopores. So that's the first part. Obviously, we understand that if we have big pores, once they are in those things, yes, we have a kind of usual fluid mechanics behavior, to a point, by the way, because we had adsorption on the walls of this. This is not a super dense fluid anyway. But yes, we can, then they're moving things. But the key message is that we needed to assess the amount of, the role and the amount of those nanopores, and they are very big. Okay, very big. It also depends on the type of chemistry. Remember that I was showing, maybe I can go back in a few slides, this one here. You see, these are different Kerogens. So the Marcellus is very, very mature. It's made only of nanopores, up to 2 nanometers. So in that thing, there's no Darcy. The Eagle 4 is very immature. So it is a young Kerogen. So maybe that's the Marcellus in maybe 300 million years. Eagle Ford is maybe, I don't know, 100 or 50 million years. So meaning that in those guys, yes, you have a big pores. But the thing also is that if you look at the texture, is that not nanopores are big, yes, but not connected. So the transport property will have to happen through the nanopores. So in that sense, Mr. Darcy, you are still mistaken, yes.
Okay, so yeah, thank you. That was a good explanation. Yeah, it was a very interesting seminar.
Thank you.
So we have a question from Huang Wen.
Hello, Juan Wen.
Thank you, Professor, for the interesting talk. I just want to confirm something about the lower bound of the nanopores. So you said like it's around 0.1 nanometer. It's like 1 angstrom, right? Is it a little bit small? For...
No. It's actually more. Actually, okay, you have to define the thing. When you do this process, sorry to interrupt you, but it's a matter of what you define, because this is me being a methane molecule when I start touching the carbon nearby, right? So you need to add on both sides a carbon side, okay, size, which is 3 angstrom. So the bottom is the methane molecule plus 3 angstrom, which is around 6-7 angstrom. Okay, correct?
Yeah, that makes more sense because it's like
of course.
1 angstrom is like smaller than CC. Right?
This is really, I mean, you need, I mean, it matters as a size, right? I mean, this is okay. So when you do actually diffraction or whatever, I mean, we usually refer to the center of mass of those atoms for those post for distribution or absorption. But in this case, we are inflating spheres up to the moment we start touching the atoms, if you like, right? Overlapping the atoms. So that's, we need to add to compare with adsorption things I was showing at some point. So you need to add the carbon atoms, and then the bottom, the smallest, is maybe like 4 angstrom, 6 or something else. Okay.
Yeah. Another question is about the amount of methane produced in lignin that will be produce more methane than cellulose over time, right? Was that aside to the more order structure of cellulose compared with lignin?
It's not so much of the you're talking about the crystal structure, right?
Yeah,
at the beginning. Not so much. No, it's really the composition. It's really composition. It's really within the molecule, not so much the crystal. The way they are piled. This is really within the molecule, the chemistry, the amount of oxygen you have at the beginning, and the way they are bound together, right? That makes the reactivity in the end. So it's really at the very intimate level.
So, like one last one, sorry, I have too many. For the a little bit technical, so for ReactFF, like after every Monte Carlo step, you have to resolve the charge rate, because in React it's different from other potentials.
Yes.
In that way. So is that like, so do you have to re-guess the charge distribution from the previous step? Or?
You're talking about electrostatics, right?
Yeah, electrostatic.
Okay. So ReactFF calculates the charge with this electronegativity equalization method scale. Okay, so at every step you have that thing. The thing is that we are dealing with organic molecules, right? The charge, if you try to do with I know, silica or calcium cements, stuff, then you're dealing with highly charged systems. But when you deal with organic molecules, for example, when you quantum to those things, actually we are doing right now, actually, you see that the charges carried by those atoms are like a fraction of an electron. For instance, a carbon atom in a sp2 environment, like a benzene-like or graphene-like, may have a negative charge of minus 0.1. You see? So, and that's a very good point, because as much as you have chemistry, the more you have chemistry, when I say chemistry, I mean heteroatoms like oxygen, sulfur in the business, or hydrogen, then you start localizing charges. So you see that, and they are on the edges of those pores. You see, and actually, and you understand why a mature Kerogen that has very little of those oxygen, less than 1%, is actually hydrophobic, because the dipole of water has no place to interact with those charges, because there's no charges. It is like van der Waals interaction, and actually the dispersion interaction, water with the carbon, is actually way less than the CO2 interaction in this sense. But as soon as you put chemistry back, you populate the surface with oxygen groups, then you localize electrons, and then you make the water to interact. So then you transform this otherwise hydrophobic carbon into an hydrophilic carbon. Okay.
Yeah. Thank you.
So yes, so reactive is good for that. I mean, good for that. Yes, it calculates the charge. The bad thing of reactive is it does not calculate the Coulombic interaction using eval summation, right?
Right.
Right. So that's a very drawback, but you should be, strictly speaking, doing it. The good news in this case is that we are dealing with organic molecules and the charge are small. So in the end, the organic contribution is not that big for those alkane molecules because they mostly interact through a dispersion.
Inert, I see. Yeah.
Okay.
Thank you.
I have a question. Excellent talk. So I really like seeing the picture of masculus, picofoot, and Hainsfield, the nanoporosity. And this makes me think of the idea of a footprint or a fingerprint. Like, could we then have a fingerprint of the shell where we kind of predict what the nanoporous structure would look like, given, for instance, the genesis or the origin that we know of the rock and the location?
That's actually the idea was that actually the idea was actually to set the industry. For instance, there are examples where the industry has actually bought or rented lands, like in Poland. I think it was Exxon, and they tried like crazy to do hydrofracking and never produced. Right? Why is that? Because the shale gas actually over Europe. I'm running in Europe, right? But the field of England, France, Germany, Poland is the same Kerogen, type 2 actually. Not type 3, but with different maturation because of the geology. And in Poland, this is a very immature Kerogen, meaning we are more in the red thing here, meaning that this is they might have porosity, but not connected. While in Marcellus, this is highly connected of nanopores, but at least it's connected. So this is why we were kind of trying to do for the industry is, can we assess the quality of production by looking at the whatever geological measurement in the first place, go dig in the ground, bring back some sample, analyze them and say, okay, that's a good Kerogen, that is a bad one, and not going to rent that terrain. That's it. But at the end of the day, all right, so, and by the way, those experiments are not crazy expensive because, by the way, this tomography, which for me it was a mind-blowing thing because we could see pores at the scale of nanometers. And right now, I'm asking the same friends in Marseille, they are like 30 kilometers away from here, to redo the same thing for cement. We're going to see CSH at the nanoscale. All right, yeah. But there is a bit more of technicality to play around with those things. But anyway, that's the idea. And that was my mind blowing because we were able to see nanopores. I mean, at the scale of 1 nanometer. You see, that's really the thing. And see the connectivity, because once you have the image in 3D, you can start analyzing the way they're connected, the pore size of the slip, also the way they are, the topology of the pore network, the way the pores are actually connected or not. And this is we found that, okay, type immature Kerogen, not so good because, okay, you may have big pores, fine, but they are not very much connected. So.
Mm-hmm. That's a really good point. I have a follow-up question. So at some point you're saying that for CO2 sequestration, we can use CO2 to kind of replace methane. So suggesting that if we kind of integrate CO2 sequestration and shale extraction, that would be efficient. But when we look at CO2 sequestration, what we see is that the CO2 saturated brine actually alters even the nanostructure. Like for the clays, for instance, there's this issue of swelling of the clay because of CO2 saturated brine. So how do you take that into account?
Yeah, okay, that's a very good point because now we are now in the pore mechanics of whatever we put at nanoscale. Very good. So first, the idea of the industry, to the industry, the message was, okay, use instead of water does not access for the mature Kerogen because it doesn't contain too much of oxygen. So this is pretty much, as I just said for our young colleague just a question ago, that you cannot, the water doesn't get into the pores, fine. So what can we do? CO2 does, and CO2 gas kick out and thing. And when I actually explained that to some colleagues, like maybe 10 years ago, and they say, okay, shale gas is business as usual, because I am originally from the porous material guys, the Pellenq guy, the what they call downstream, separation and all that jazz. This is known forever. Just not known by the industry of shale gas, fine. But now to address your question of swelling, yes. We do have, and this is the PhD thesis of Laurent Brochard. Maybe you remember him at MIT. He was a postdoc at some point, Laurent. Now he's doing a full career as a professor at École des Ponts in Paris. Laurent actually did his PhD with Henri Van Damme and myself and Mathieu Van Damme was really much to show the pore mechanics of CO2. And CO2 does make the carbon to swell. Yes, indeed, right? which is a good thing in some ways, because if you think of the pocket of kerogen, if you make them to swell, maybe you will actually help even the fracturing, or propagating the fracture, right? But for sure, what CO2 does in the first place is that we get rid of CO2 for a very good reason. Is that the heat of adsorption of CO2 is way larger than that of methane, not because of electrostatics, that we are still in the van der Waals interaction, because CO2 has a very small quadrupole, so if there's not much charge around, not much to say, but for sure the dispersion interaction, the van der Waals interaction of CO2, so carbon and 2 oxygen, the polarizability is way larger, and this is what drives this van der Waals interaction, and it's way larger than methane. So in the end, you have a rate of adsorption of CO2, which is maybe 25 kilojoules per mole in porous carbon, why it is actually maybe 18, 15 for methane. So there is no, I mean, at equilibrium, the picture is very clear. Methane will replace, CO2 will replace methane, right? By the way, once you have CO2 in the pores, you create some swelling of the carbon. As I said, maybe it can help the fracturing somehow, right? By creating bigger pores. Yeah.
Okay, so that's a very interesting discussion. Do we have either additional question for our speaker?
Just a brief question. Outstanding lecture, by the way, Ron. Can you predict the effect of anisotropy due to pressures, different directions?
Okay. In the ground, right? On the ground.
Underground, yeah. That's
okay.
That's an important aspect in simulation of fracking.
All right. Oh yeah.
And then of course changes of pressure create anisotropy.
All right. So okay. That's very good question.
That would be the key of starting cracks normally to the primary crack plane.
Okay, all right, okay, I see your point. So at the scale of so those experiments were at the scale of 200 nanometers.
Your samples are taken horizontally from the shale, or
okay, so there is no direction in there with subsumed bulk, but yes, we can actually put them in anisotropic. So we can do an NPT simulation of those. We fix a pressure, but this pressure doesn't have to be the same in all directions. So we can have a PZZ pressure, which is larger than the rest, for instance. And that will simulate this bedding plane or whatever it's called. The idea that, yes, you have a pressure in one direction, which is, and obviously what I can tell you is that how much, I mean, I don't know the way how to orientate the big pores in the first place, because obviously the mechanics, the response will be linked to the way those.
By the way, Roland, the picture of the Marcellus shale.
Yes.
There was horizontal cross section. From the original.
No. I mean, this is right in the middle of the kerogen. So the way we actually extract the sample.
Yeah, but I suppose that in a vertical section will be anisotropy.
But that's not at the scale. The box size is actually 200 nanometers, so it's very small. So we actually the way that my colleagues did, actually they extracted a sample of the kerogen in a big micron, 50 micron nest of kerogen. So it's really at the core. Now, what I cannot answer you is if they traced somehow they noticed the orientation of the sample. What I can tell you, if you make it to turn, for instance, the Marcellus, you see no orientation of the pores.
Yes.
Okay. There are at that scale there is no particular orientation of the pores, at least for the super nanopores. Okay. They are in all directions in 3D. Okay.
On Hensfield also same thing.
Yeah, and that the Hensfield is the same. Hensfield is a mature kerogen, it's a bit like Marcellus. You see, the what we see is at least 1 nanopore. So okay, that's the lowest they can do, and you see that the pores are in all directions. Really, there is no particular things. Okay. But yes, in simulation we can actually play around with an isotropic pressure field. Actually, yeah. Yes,
okay, thank you.
Okay, thank you very much, Roland. This was a very interesting talk. Yeah. Thank you everyone who stayed until the end. We went ahead of the allotted time, but that was an amazing discussion. So thank you everyone, particularly our speaker Roland, and we'll see you another time.
Thank you guys.
Bye-bye.
Take care. Bye-bye. Thank you very much for the invitation. Bye-bye.